All right, so play catch up here since my technology was not working. All right, we're doing a good job getting our stickers up there. Okay, I think that I finally got this now that it's working. See if I can get this to work. No. There we go. Yay! It's functional now. All right, almost got all the dot stickers up.
lines are like fairly straight.
Hmm?
The lines are like fairly straight.
Yeah, they are. We're doing a good job. Yesterday we were a little bit
really
off.
bad.
We did okay. We did all right. I'm not going to say we did more than okay, but we did okay. All right, so I'm adding the ones up here for the people that are out. Come on. We need to go all the way down. There we go. Let's see how many more stickers I need to put up here. All right, I think I about got it. Ooh. Somebody can't divide. Don't know who. Somebody's got put in the wrong spot. What do you notice about today's graph versus yesterday's graph? I can't see.
It's straighter.
It's straighter. It's basically the same graph, right? I want you guys to copy this, again, basic shape, into your notes. Yesterday, we had the sampling distribution of X. This is the sampling distribution of, is it still X? The proportion, oops. Okay, so it's of a proportion. Is it the proportion of the whole population or the proportion of samples? Of samples. So what's the notation that I would use to indicate a proportion of samples? P hat. This is the sampling distribution of P hat. So this is the proportion of orange candies in a sample of 50. What does each dot represent now? That's okay. One sample of 50 Reese's Pieces. Because we took a sample of 50, right? One sample of 50 Reese's Pieces. And the proportion of orange candies. All right, let me see if I can get a picture up. Get this on the screen. There we go. Now we got our graph up there. Okay. Find the new mean and the new standard deviation. Does anybody need me to go back to? All right. Hot. Yeah, I can go back now. I got it to work. It worked while you guys were putting your stickers up there, which is the only reason we're going to have a video today. So there's not a video of the first part, but there is a video of this part now. One sample of 50 Reese's Pieces and the proportion of orange candies in that sample. How would we find the new mean? What was our old mean when we were just doing number of candies? 20. And what did we do to each of ours to find the proportion? We divided the number by 50, the number in my sample, right? So let's try the same thing here. Mu for p hat is equal to my old mean divided by 50, which is just how much? 0.4 or 0.40, depending on how you want to write that. When I do the mean for p hat, we do n times p, but then we're dividing it by n. So my n's cancel out. That means that the mean for p hat is just whatever p is. Standard deviation. What do you think we need to do to our standard deviation? Divide it by 50. So sigma of p hat is equal to 3.464 over what? Over 50. Tell me what you get when you divide that. 0. You said what? 3.464 divided by 50. 0.06928. Beautiful. When I want to find the standard deviation of p hat, let's think about what we just did there. So sigma for p hat, this is going to be my formula that I use. I've got the square root of n times p times 1 minus p over, if I'm dividing by n here, if it goes underneath a radical, it would become squared, right? That'd be n squared. But the n in my numerator is going to cancel with one of the n's in my denominator. So the formula that we use to find standard deviation for p hat is p times 1 minus p over n. What do you think the shape would be? The approximate shape of the sampling distribution. Large counts. So what would we be checking for large counts here? How would I do large counts? What did we do before? Yeah. N times P has to be greater than 10 or equal to 10. And N times 1 minus P has to be greater than or equal to 10. So do my large counts change at all here? Nope. I'm going to have 20 is greater than or equal to 10. 30 is greater than or equal to 10. This is the same as before. So what's my approximate shape then? It's approximately normal. Uh-huh. So the issue is that sometimes we're not going to be doing the sampling ourselves, and we will only have what P is for the population. In that case, we need to know that the mean for P hat is exactly the same as the mean for the population. Or sorry, the mean for P hat, mu for P hat, is the same as the population proportion. My bad, I misspoke there. Right, do not forget, when we are talking about something that is normally distributed, you need to have the n, and then your mean and your standard deviation inside parentheses. And I usually go ahead and label those. I would highly recommend doing that. We know that a bag of Reese's Pieces contain exactly 40% that are orange. If we select a random sample of 50 candies, what's the probability that the sample proportion will be 50% or greater? How would I find the probability that the sample proportion would be 50% or greater? Inverse norm is when I have the area under the curve. When I'm looking for a probability, we're just going to do normal CDF. So this is what my normal curve looks like. I have my mean, I have my standard deviation. What's the probability that the sample proportion is 50% or greater? Well, that's going to have to go, or sorry, that shouldn't be a 0.20, that should be 0.40, my bad. Sorry, guys. I was looking at 20 candies. Where would 50% go on my picture? Right in the middle of this one? My mean on this is 40%. A little further to the right. 50% is going to be over here somewhere. And I want the probability that's 50% or greater, so which way would I shade this then? Shade it to the right. So then how am I going to figure this out? The probability that P hat is greater than or equal to 50% is what? Your probability notation on these is super important. If you're not using probability notations, the probability of what it is that you're finding, you guys are losing points. You're leaving points on the table. You have to have your probability notation. Normal CDF. Normal CDF. And what would I put in first? 0.5, because that's my lower bound. What should come next? A big number. You guys okay with like 1,000? Because if my mean is a 0.4 and I got 0.5, like 1,000 should be big enough, right? There's my upper bound. What comes after my lower bound and my upper bound? The mean, so 0.40. And after the mean, standard deviation, so 0.06. 928. So the probability that in my sample, p hat, I have a proportion of 50% or larger is about what? Point what? 0.141. Let me double check on my own calculator because I didn't do this yet. Oh, I got something smaller than 0.141. .07, what were the last two? 445. Yeah, that's what I got also. I would double check where your decimal points went. Probably in the standard deviation, that would be my guess. All right. Let's look at the next page. All right, so for p and p hat, mean and standard deviation, the mean of p hat is whatever p is, so whatever the population proportion is. Sigma of p hat is the square root of p times 1 minus p divided by n. I can only use these formulas if the 10% condition is met. If I don't have independence, if I haven't met the 10% condition, I can't use those formulas at all. So this is super, 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 super important. We're approximately normal if the large counts condition is met. So n times p has to be greater than or equal to 10. N times 1 minus p has to be greater than or equal to 10. This is what is going to allow me to solve problems, because I can say that the distribution is approximately normal, and then I can use normal CDF. This is if you want to do it by hand and use table A, then you have to find your z-score instead of using your calculator. So that's how we convert to a z-score. We would have our p hat minus p over, and then that would be my standard deviation formula there. I want you guys to go ahead and try to check your understanding. Let's take about 5 minutes. All right. What is the mean of the sampling distribution? 0.08. It is whatever the proportion is for the population. Calculate and interpret the standard deviation of the sampling distribution of p hat. Check that the 10% condition is met. What is my standard deviation? Yes. I rounded it to 3 decimal places, so I got 0.009, but yes, I usually prefer it to go out a little bit further. I just only had so much space there. How would we interpret that? Very close. The sample proportion of adults, because remember, this is standard deviation of p hat, so the sample proportion of adults that have never had a cavity typically varies by 0.009 from the true proportion of 0.08. Have we met our 10% condition? Yes. We have a random sample of 1,000. My population is all the US adults. There are at least 10,000 adults in the US, so I know my 10% condition has been met. Is the sampling distribution of p hat approximately normal? Yes. We check n times p, that comes out to be 80, that's greater than or equal to 10. N times 1 minus p is 920, so it's definitely greater than or equal to 10. So the sampling distribution of p hat is approximately normal. I'm going to pop that up a little higher on the screen. What would I need to do to find the probability that the random sample of 1,000 adults will give a result within 2 percentage points of the true value? What kind of distribution did we say we just had? Approximately? Approximately normal. So anytime we see approximately normal, what's the first thing I want to see on your page? The shape. I want to see your artwork. So we're going to have a normal distribution. We know the mean, 0.08. We know the standard deviation, 0.009. Within 2 percentage points, so within 0.02. So I add 0.02, that takes it up to 10%. And I minus 0.02, that takes it down to 6%. What would I want to do from here? Now that I've got my picture all drawn out, what would I do next? Normal CDF. Normal CDF, 0.06 would be my lower bound. 0.10 would be my upper bound. My mean is 0.08. My standard deviation is 0.009. When I pop all of that into my calculator, I get what? What does that give me? .974, 0.9737, or 36, depending on which way you do it. If you do it by hand, you get .9736. Doing it by hand, you have to calculate the z-scores for both of them. Then you have to subtract them and then look it up on table A and then subtract. Lots of work. I would just do it on the calculator. If the sample size were 9,000 rather than 1,000, how would that change the sampling distribution of p hat? Would the shape change? Would it somehow be not normal anymore? Nope. My large counts would still be met. Would my mean stay the same or change? How do we find the mean of p hat again? Yeah, it's going to stay the same because it's just going to be my population proportion. What about my standard deviation? That one's going to change. Because in my standard deviation formula, we divide by n. The mean for p hat is whatever my population proportion is. It's whatever p is. But the standard deviation, we do p times 1 minus p divided by n, and then we square root it. So what happened to my overall standard deviation by increasing my sample size? Standard deviation got smaller. Bigger sample, smaller standard deviation. It gets narrower. We have less variability. Homework due date has been changed to Friday. Tomorrow, we're going to look at another simulation. If you have a Chromebook or a laptop, please bring it to class with you tomorrow. Is there a way to do what we're doing on the phones? Yes, but I'm going to have to give extra directions. So please bring a device with you that is not just your phone. Please bring a Chromebook or a laptop.